Hello, my name is Justin Cummings. In this video, I am going to be demonstrating an outline of the proof that the Gaussian integral is equal to the square root of pi. The Gaussian integral is defined as the integral from negative infinity to infinity of e to the negative x squared dx. To compute the Gaussian integral, we're going to be observing the square of the Gaussian integral. So we're going to be observing integral from negative infinity to infinity of e to the negative x squared dx squared. Now we're going to expand this in the following way. We'll keep the variable as x on our first term, and for the second term, our variable is going to be written as y. Since this is just a dummy variable, it does not change the actual value, so we can do this. Now, properties of integrals say that the product of two integrals is equal to the double integral of the product of the integrands. So we have that this is equal to the integral, double integral, both bounds being negative infinity to infinity, of e to the negative x squared dx, e to the negative x squared times e to the negative y squared times dx dy. And by properties of exponents, we can rewrite the integrand as e to the negative x squared plus y squared dx dy. Now we're going to transfer this integral from Cartesian coordinates into polar coordinates. And to do that, we are going to have to look at what we are integrating over. So if we're integrating with y going from negative infinity to infinity and x going from negative infinity to infinity, then we're just talking about the entire Cartesian plane. Now, to get to any point on the Cartesian plane using polar coordinates, we're going to have to be able to go in any direction for theta, and we're going to have to go at any magnitude for r, which means that theta is going to span from 0 to 2 pi, and r is going to span from 0 to infinity, 0. Which means that our bounds in the double integral with polar coordinates are going to be from 0 to 2 pi and from 0 to infinity. And in polar coordinates, since x is equal to r cosine theta and y is equal to r sine theta, we have that x squared plus y squared is equal to r squared. And in polar coordinates, dx dy is equal to r dr d theta. So we end up with the integrand being e to the negative r squared r dr d theta. And this double integral is much easier to compute than this one, because we could just use u substitution right here on r squared. So we'll end up with integral from 0 to 2 pi of the antiderivative of this is going to be negative 1/2 e to the negative r squared. We're going from 0 to infinity, d theta. Now when we plug in infinity, this is going to be 0. And when we plug in 0, we get e to the 0 is 1, so negative 1/2. So we're subtracting negative 1/2, we get positive 1/2. So we have that this is equal to the integral from 0 to 2 pi of 1/2 d theta. And of course, this is just going to be 2 pi times 1/2. So this is equal to pi. But this is the square of the Gaussian integral, so that means that the actual Gaussian integral is going to be equal to the square root of pi. So when I first saw the Gaussian integral in my calculus class, I didn't think that it was anything more than just an exercise to practice solving integrals. But when I started studying probability and I was introduced to the normal distribution, I saw the use that this computation gives us, because the density function of the normal distribution is defined by the Gaussian integral. And the normal distribution is very useful because the central limit theorem states that whenever you have a sequence of independent and identical trials, you can have a distribution for the amount of successes that can be computed using the normal distribution. And having a sequence of identical and independent trials is something that's very common in real-world applications. So that is the Gaussian integral. Thank you.